Properties of determinants. Here there are more properties for determinants. Property number one, the determinant of a matrix where each entry in that matrix is multiplied by the same scalar. That scalar can be factored out based on the number of rows that you have. It becomes that factor, that scalar, raised to the power of n, raised to the number of rows. Here the number of rows equal the number of columns, so n equals to n. So that determinant then would be, if it's a k factor times each entry in the matrix, you can factor out that k factor, k to the third, times then the determinant of the matrix A itself. So for an example, if we have this matrix here that's given, and notice that there's a factor of 3 in each of the rows. We factor out a 3 from the first row, that's times 3. Factor out a 3 from the second row, that's 3 to the second, and then we factor out a 3 from the third row, that's 3 to the third. Now what I do is just find the determinant of the matrix that's left. And I do that by cofactor expansion along the second row, and that gives us the negative 2025. Property 2 is probably, I think, very important, and I think it's important because a lot of times certain assignments, textbooks, exercises would try to trick you with this. It kind of seems like it should be equality, but it's not. And that is that the determinant of the sum of two matrices, the determinant of A plus B, is not the same as the determinant of A plus the determinant of B. In web assign, you'll be asked to do some exercises to show that this relationship is not equal. Here I give an example. This is my classic example. If you take this matrix A and find its determinant, the determinant of A is 1. Why do it do that? So this is 1. And then we find the determinant here of B. It's also 1. Now, if I add A plus B, I get the 0 matrix. Thus, the determinant of the 0 matrix is just 0. Right? Well, but the determinant of A plus the determinant of B, well, that's 1 plus 1, that's 2. That cannot equal to 0, which was the determinant of A plus B. So the inequality holds. Right? And you can do that for any two matrices of the same size. And you will see that in web assign. It's like blah, 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 blah. And you will see it. This relationship will not be equal. Right? Pretty neat. You kind of think that it's supposed to be equal. Property 3, if A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of A times B is 1. If A and B are matrices of the same size, then the determinant of is equal to the determinant of A times the determinant of B. Pretty neat consequence. We use that to develop property 4, and property 4 is what we actually want, and that is that if I have the determinant of A, can I easily get the determinant of A inverse? Well, yes, you may, based on property 3. Here, if the matrix A is invertible, then the determinant of A inverse is equal to 1 over the determinant of A. And I put the proof here of that consequence. Typically, freshman, sophomore students are asked to prove that. You just mimic my proof there. I use property number 3, and also something that we know about the inverse of a matrix. So if A is invertible, that means that A inverse times A is equal to the identity matrix. Now what I do with this statement here is I just take the determinant of both sides. And taking the determinant of both sides, I use property 3 to break down this product. So property 3 says that the determinant of A inverse times A is the same thing as the determinant of A inverse times the determinant of A. Now the determinant of the identity is just 1, and so you get what you need. We're going to use that to just work a problem here just to show that that makes sense. So here, find the determinant of A inverse by only finding the determinant of A. So that simply means we want to use the determinant of A inverse is equal to 1 over the determinant of A. So all we need to find is just the determinant of A. So we find the determinant of A. I'm just going to use cofactor expansion along the second row. So we get negative 1 times 5 minus 3, and this is 2 minus 2. So we get negative 5 for the determinant of A. So if that's the case, then the determinant of A inverse is equal to 1 over the determinant of A. Well, this is just negative 1 over 5, or 1 over negative 5, which is the same thing as negative 1 over 5. Property number 5. Here, the determinant of a transpose, if A is the square matrix, then the determinant of A is the same as the determinant of A transpose. So this is the same matrix here in the previous example, and from there we found that the determinant of A was equal to 5. So now I'm just going to verify property 5. So in other words, okay, we've shown this. Now let's see if we can show this. So we find A transpose, and then we find its determinant. Remember the transpose, you just interchange the rows and columns. So now, I'm going to find the determinant of A transpose. Just going to find it directly, and then we can check to verify to make sure that's equal to 5, right? So I got a 0 here and I have a 0 there. I'm going to use cofactor expansion along the third row. So you remember the signs would be plus, negative, plus. So it's going to be a negative 3. Delete this row and column. So we'll get 1, 2, 1, 2. Then I come to the 5. Plus 5. Delete that row and column. So it's just 1, 2, 0, negative 1. So this is negative 3 times 2 minus 2. So that's 0. Plus 5 times negative 1. Let's see. Should be positive 5. Oh. Oh, I get negative 5. Let me go back and check that other one. I think I was wrong. Oh, no, I got it. I'm sorry. We got the determinant to be negative 5. I don't know what I was thinking. Okay, good. So it's negative 5. Okay, so I'm using that matrix from here, so I need to write this determinant is negative 5. Oh, I'm sorry. I was about to lose it. Okay, so we get negative 5 and negative 5. Okay, everything is good. Yep. So you know, going forward, you really don't have to do all that. If they ask you to find the determinant of A transpose, then you just find the determinant of A, if that's easy. And then these determinants will be the same thing. Yep. What this chapter does, that first section is somewhat, you know, there's more to it. The next two sections, there's hardly anything there. But then the last section in chapter 3, it's like they got everything there, right? And so it's like they were saving up all the ammunition for the last section. That is crazy. So these sections are kind of short. I'm going to break up that last section into parts. So I have 2 or 3 videos for each subtopic there in that last section. Thank you.